Welcome. Let's get into our this next week. So based on what we were doing last week, we're going to continue with sets. We're going to talk about power sets. So a power set is a set of all subsets. As a quick reminder, so if I give you these things, I don't want to find the subset, the power set for each of these. The power set, for instance, A, I'm just going to do this real quickly. The power set of A is going to be the set of the sets circle, triangle, square, circle, square, circle, triangle, triangle, square, and then also the three, and then we have the sets just circle, just triangle, and just square. And then we don't forget we always have the empty set is always a subset. So this would be the set power set for A. Consider for a second just what's the power set of C? So the power set of C is really the power set of the empty set. Well, that's going to be the empty set, and that's it. It actually has nothing else. But if I did this thing right here, ironically, the power set of D, again, set notation is critical. This is actually the set that includes the empty set and the empty set. That would be this power set. I won't do number two. I think all of you can kind of figure that out based on what we have. And so power sets are kind of a valuable thing. So we're going to move our transition to doing proofs into what if we have power sets? So I'm going to do this first one, and then I'm going to let you do as part of this one sets 2.3.26, 3.27, and then 3.28, which is actually just finding a counterexample to 3.27. So this is, we have a subset going one way, and it's just pretty much saying, why is there not equality between these things? And there's some reasons why. So this first one is if I have the power set, the intersection of power sets is equal, and I'll give you a hint on this in just a little bit, to the power set of the intersections. But let's just come back here to this one. So there's a couple key things you have to note. This is an if and only if, which really means that I have two directions to go. I have to start with S being a subset of T, and then I have to go over to this side. And then I have to start with this side, and I have to come back and show that if I have the power sets or subsets of each other, then S must be a subset of T. So the way that we normally do this when you're, and I've seen this written a lot of ways, is often they'll write it this way. They'll break it into, they'll do like an arrow, and they'll do this. And this means, all right, so we're going to suppose that PS, I don't mean a straight line. We suppose that S is a subset of T. And we want to show, we want to get down to the point where we show, therefore, the power set of S is a subset of the power set of T. Now, how do we do that? Well, we essentially have to show, because S is a subset of S, then we say, okay, let's suppose that, so suppose this is true. Now consider A, which is inside the power set of S. So that means that A is a subset of S by definition. Okay, so I just did this. So A is actually a set, but I'm calling it like it's an element. I need to show, if I can show that it is an element in the power set of T, then we're good. But since A is a subset of S and S is a subset of T, then by what we proved last week, A is a subset of T by the transitivity that we proved last week. Okay, so we proved this, and since A is but so but then A is an element in the power set of T because it is a subset. So because A is a subset of T, it is a power set. So notice this is the key thing. Really, this proof kind of and because A was arbitrary, we actually get the following conclusion. But the key part is I'm manipulating the fact that in power sets, A is an element, and in terms of S, it's a set. So I'm kind of moving back and forth and using those two subtle differences to kind of benefit myself in this idea. So this would be the first proof, first direction. To prove it the other way, again, we prove it this, we do like arrow this way. And what that is I'm gonna say, all right, I'm gonna suppose that the power set of S is a subset of the power set of T. Well, I need to show from that that A is a subset. I mean, S is a subset of T. Well, how am I going to do that? Well, we can do that actually by doing a proof by contradiction. So I'm going to suppose this. Now to do a proof by contradiction, suppose also that S is not a subset of T. So I'm just saying, let's suppose it's not a subset. Because remember, if this is true, it should imply that the other side is true. But if I'm looking at the contradiction situation, which is the only situation that would break our if then statement. I could also do this via a contrapositive, which is again showing that if S is not a subset of T, then the power sets are not subsets. We can do that. There's lots of different approaches on this one. But if I do this, all I need to show this leads to a contradiction. Well, since S is not a subset of T, there exists some X in S such that X is not in T. Otherwise, that's the definition, that it's not a subset if there's something that's not in the larger set. Well, now, so let's suppose it's true. So let's then, all right, then the subset, then, I should say not then. I really want to do I want to say let's suppose then. All right, or consider. I'll do another consider because I want to consider consider A a subset of S such that X is an element in A. So I'm now letting A be just any subset in X be any element, A be any subset in S as long as X is in there. Well, since X is not in there, then all right, but since X is in A, then A is not a subset of S. Sorry, not a subset of T, I should say. Oh, that was my bad. It's not a subset of T. Oop. Hit the wrong button. Not a subset of T. And since S is not a subset of T, then A is not in. That was a horrible not in. A is not an element in the power set of T. But A is an element in the power set of S. So by definition, the power set of S cannot be in the power set of T, which is a contradiction. So this is where we use the proof by contradiction to our advantage to kind of show this. And I know this is getting a little lengthy and I'm writing this all out, but I wanted you to kind of see how this is going to play out in when you're working on it. So we can type these things up and we can kind of write it out. We got to work with this in a lot of different ways and kind of this is where perhaps instead of doing this, like doing a contrapositive would been better and just said, okay, let's suppose that S is not an element, is not a subset of T, and then show that then the power sets aren't, so we can just do the contrapositive. But the if and only if is where it gets, you got to do two directionalities or essentially two proofs for one theorem. Now, the truth is you have the same exact thing when you go to this. So that equal sign right here is actually an if and only if. Whenever we're dealing with sets, because that's what power sets are. Power sets are just sets. You're really going to need to show two things. You're going to need to show that the power set of S intersect power set of T is a subset of the power set of S intersect T. That means show that anything that's over here is over here. And then you got to do the exact same thing, but just reverse the order. So now start with something over in the power set of the intersection and show that's in the intersection of the power sets. So you got to start and do both ways. So equality is actually extremely hard because it's the same as if and only if. It's actually a two-way proof, and two-way proofs are crazy hard because it's not uncommon that you have ease with one of the directions and the other direction just gives you a headache. So as you're working through this, kind of ask questions. I'm really curious to see how you all attack this one. And then the next one is just a one way. So I just have to show that anything that's over on the left hand side, anything in the union of power sets is inside the power set of their unions. And then this where this question comes in. So we have to show something that, give an example where there's something in the, so again, I got to simply show there's something inside the power set of unions that's not necessarily in the union of their power sets. So is there such a situation that we can come up with? But also, this is the question I have for you is also, is it ever true? In other words, is there sets S and T where this would be true and so forth? So this is kind of a deeper question. I want you to really think on this and chew on it and come up with some really good answers. All right. Good luck. And as usual, let me know what questions you have.